There is a moon in this solar system where it rains, where rivers carve valleys into the landscape, where thick clouds drift across a sky filled with nitrogen, where seas stretch to the horizon under a hazy atmosphere denser than our own. Everything about this world sounds familiar. Everything about it feels like something you already know. And that is exactly what makes it terrifying. Because this moon is not a warm place. It is not a living place. It is a frozen nightmare dressed in Earth's clothing. A world where the rivers run with liquid methane at -179 degrees Celsius, where the rain would freeze your blood on contact, and where the landscapes you recognize are built from materials that have nothing to do with life as you understand it. This is Titan, Earth's dark twin. If you enjoy exploring the strangest and most unsettling places in the solar system, hit like and subscribe. We go deep into the science that actually matters. Are you comfortable? Now, let's begin. For most of human history, Titan was nothing. A tiny point of light wobbling next to Saturn, visible only through a telescope, interesting only to the kind of person who spent entire nights sketching the positions of specks that most people could not even see. The Dutch astronomer Christian Huygens found it in 1655 using a telescope he had built with his brother. He called it Saturni Luna, Saturn's moon. That was it. One moon, one name. One faint dot in the eyepiece of a handmade instrument, orbiting a planet so far away that light from the sun takes more than an hour to reach it. For the next 300 years, that is all Titan was, a dot. A catalogue entry, a minor member of a growing list of moons that astronomers kept discovering around the giant planets. Nobody had any reason to think it was special. It was not the largest moon in the solar system. That title belonged to Ganymede, orbiting Jupiter. It was not the closest to its parent planet. It was not the most reflective. It did not have any obvious features that made it stand out. Saturn had rings. Saturn had mystery. Titan had a position in a table. Then, in 1944, a planetary astronomer named Gerard Kuiper pointed a spectrograph at Titan and detected something that nobody expected. Methane. Not on Saturn, not in the space around Saturn, on Titan itself, in its atmosphere. That single detection changed the trajectory of planetary science. Because moons were not supposed to have atmospheres, not thick ones, not detectable ones. Earth's moon has essentially nothing. The Galilean moons of Jupiter, massive as some of them are, hold only the thinnest traces of gas. Yet here was Titan, a frozen body orbiting a planet nearly 10 times farther from the Sun than Earth, and it was wrapped in methane gas thick enough to be measured from across the solar system. For the next 3 decades, the question hung in the air like the gas itself. What else was in that atmosphere? How thick was it? What was the surface like underneath? Nobody could answer because nobody could see through it. Every telescope pointed at Titan returned the same result, a featureless orange sphere, smooth, opaque, giving away nothing. The first real attempt to crack the mystery came in 1979, when Pioneer 11 flew through the Saturn system. It gathered limited data, enough to confirm that Titan was cold, that the atmosphere was significant, and that there was far more going on than methane alone. But Pioneer was not designed for Titan. It was passing through. The real revelation came a year later. In 1980, Voyager 1 arrived at Saturn. Its trajectory had been deliberately designed to bring it close to Titan, so close that the encounter would bend the spacecraft's path out of the plane of the solar system entirely. NASA considered Titan important enough to sacrifice Voyager 1's ability to visit Uranus and Neptune. That decision tells you how seriously scientists were taking the atmosphere question by then. Voyager 1 passed within 4,000 kilometers of Titan's surface, and what it found was, in the most literal sense, unlike anything encountered at any moon before. The atmosphere was not thin. It was not a wisp of gas clinging to an icy surface. It was massive, dense, deeper and heavier than the atmosphere of Earth itself. Surface pressure on Titan measured approximately 1.47 bars. That is roughly 50% higher than atmospheric pressure at sea level on Earth. Stand on Titan, and the air above you weighs more than the air above you on the surface of your own planet. On a moon smaller than Mars, a moon orbiting a gas giant nearly 1.5 billion kilometers from the Sun, the primary component was not methane, as Kuiper's original detection might have suggested. It was nitrogen, roughly 94% nitrogen. Earth's atmosphere is roughly 78% nitrogen. That overlap stopped researchers mid-conversation. Two worlds, separated by more than 1 billion kilometers of freezing vacuum, both breathing the same dominant gas. But Voyager 1 could not see the surface. The atmosphere was too thick. The haze was too dense. Layer after layer of organic aerosols, tiny particles of complex hydrocarbons formed by ultraviolet light breaking apart methane molecules high in the atmosphere, created a smog so opaque that visible light simply could not penetrate it. Titan looked like an orange billiard ball, smooth, featureless, and deeply frustrating. Scientists knew the atmosphere was there. They knew it was substantial. They knew it was nitrogen-rich with methane mixed in. They could measure temperature. They could measure pressure. But the surface, the actual ground of this world, remained completely hidden. It was as if the moon had drawn a curtain around itself and refused to let anyone look inside. For the next 2 decades, Titan sat in the scientific imagination as one of the most tantalizing, unsolved problems in planetary science. What was underneath that haze? Rock? Ice? Oceans of liquid hydrocarbons? Some scientists speculated that the entire surface might be covered in a global ocean of ethane and methane, hundreds of meters deep, fed by billions of years of photochemical production in the atmosphere, raining down liquid hydrocarbons that had nowhere to go but accumulate. This was not a fringe idea. It was a serious, published hypothesis supported by respectable atmospheric models that predicted more liquid hydrocarbon production than the surface could plausibly absorb into a solid crust. Others predicted a dry, frozen wasteland coated in organic sludge that had rained down from the atmosphere over billions of years and solidified into a dark, tarry crust. Still others suggested a mixed terrain, with some areas dry, some areas liquid, and some areas buried under drifts of organic snow. The debate was fierce, detailed, and completely unresolvable with the technology available. No telescope on Earth could see through the haze at visible wavelengths. The atmosphere was a locked door, and nobody had the key. Then, in the mid-1990s, a partial key appeared. The Hubble Space Telescope, orbiting above Earth's atmosphere, was equipped with infrared instruments that could observe at specific wavelengths where Titan's atmospheric haze was slightly less opaque. These narrow infrared windows, gaps in the absorption spectrum of the methane and aerosol layers, allowed tiny amounts of surface-reflected light to escape into space. The images were crude by modern standards, smeared and pixelated, showing only the broadest contrast differences across Titan's disk. But they were enough. Hubble revealed that Titan's surface was not uniform. There were bright regions and dark regions. One particularly bright area, centered near the equator on the leading hemisphere, was large enough to be mapped even at Hubble's limited resolution. Scientists named it Xanadu. It appeared to be a continent-sized bright feature, possibly elevated terrain coated in cleaner water ice, contrasting against the darker materials surrounding it. The dark regions could be anything. Liquid hydrocarbon seas, flat plains of organic sediment, low-lying basins coated in accumulated tholin material. The resolution was too low to tell. But the mere fact that Titan had surface heterogeneity, that it was not a featureless globe but a world with distinct regions, transformed the scientific conversation. Titan had geography. Whatever the surface was made of, it was not the same everywhere. Those Hubble images fueled a decade of increasingly heated speculation and drove home the urgency of sending a dedicated mission. The arguments between the global ocean camp and the dry surface camp intensified. Each group could point to certain features in the infrared maps as supporting their model. Neither could prove the other wrong. The surface remained tantalizingly just beyond the reach of definitive observation. That changed on October 15, 1997, when a Titan 4B rocket launched from Cape Canaveral, carrying the most ambitious outer solar system mission ever built, Cassini-Huygens. A joint mission between NASA, the European Space Agency, and the Italian Space Agency. Cassini was the orbiter, designed to spend years circling Saturn and its moons. Huygens was the probe, designed to do something that had never been attempted before: drop through Titan's atmosphere, descend to the surface, and send back data from the ground of a world nearly 1.5 billion kilometers from Earth. The journey took nearly 7 years. Cassini-Huygens arrived at Saturn on July 1, 2004, and began a systematic study of the entire system. But Titan was always the crown jewel. Cassini carried a radar instrument capable of piercing the haze and mapping the surface below. It carried infrared cameras that could see through narrow windows in the atmospheric absorption spectrum where the smog was thin huygens to allow light through. And strapped to its side, waiting for its moment, was Huygens. On December 25, 2004, Huygens separated from Cassini. It drifted for 20 days toward Titan. And on January 14, 2005, it entered the atmosphere at a speed of roughly 6 kilometers per second. The entry probe punched into the upper haze layers, decelerating violently. A pilot parachute deployed, pulling away the aft cover. The main parachute opened, slowing the descent dramatically. Instruments began sampling the atmosphere immediately, measuring temperature, pressure, composition, and wind speed at every altitude as the probe drifted downward through the orange murk. The descent took approximately 2 hours and 27 minutes. For the first portion, under the main parachute, Huygens dropped slowly through the stratosphere, recording data from the thick haze layers that had hidden Titan's surface from every telescope ever pointed at it. The atmospheric composition readings confirmed nitrogen and methane, but also began detecting trace gases, the complex organic molecules produced by photochemistry in the upper atmosphere, drifting down through the layers like an invisible toxic snow. At roughly 125 kilometers altitude, the main parachute was jettisoned and a smaller drogue chute deployed to increase the descent rate. The mission timeline was limited by battery life and the geometry of Cassini's relay pass overhead. Huygens had to reach the surface before Cassini disappeared over the horizon and the communication link was lost. During the descent under the drogue, Huygens dropped through the troposphere, the weather layer, where methane humidity increased sharply. The temperature continued to fall. Clouds of methane ice particles drifted past. The light filtering through the haze shifted and dimmed. And then, in the final kilometers, the atmosphere cleared enough for the descent imager to see the ground. The scientific community watched the data arrive in near real time, relayed through Cassini with a delay imposed by the vast distance between Saturn and Earth. The images appeared on screens at the European Space Operations Center in Darmstadt, Germany, and simultaneously in laboratories and control rooms around the world. Researchers who had spent decades arguing about what Titan's surface looked like were about to find out. The room was silent as the first surface images resolved. What those images showed was not what anyone had predicted. It was stranger. It was more familiar. And it was deeply, immediately, unsettling in a way that took years for the scientific community to fully articulate. The camera on Huygens looked down as the probe descended and saw a landscape, not a featureless plain, not a frozen wasteland, a landscape with topographic variation, with bright highlands and dark lowlands, with networks of narrow channels connecting elevated terrain to flat basins below. The scientists watching the images arrive recognized the pattern immediately. These were river valleys, channels carved by flowing liquid, channels cut by flowing liquid, branching and merging in the same dendritic patterns that rivers on Earth create when rain falls on sloped terrain and finds its way to lower ground. When Huygens landed, it did not bounce, it did not skid. It settled into the surface with a soft, damp crunch, the instruments registering a material that yielded under the probe's weight like compacted wet sediment. The temperature at the surface registered approximately -179 degrees Celsius. The camera on the ground showed a dark, flat plain, scattered with rounded pebbles and cobbles of water ice, worn smooth by something. The sky above was a deep orange-brown, dim, hazy, but not dark. There was light, diffuse, scattered, filtered through hundreds of kilometers of smog, but enough to see by, enough to cast faint shadows, enough to create something that looked hauntingly like a gloomy afternoon on a very alien beach. Meanwhile, Cassini's radar began to peel back Titan's secrets from orbit. Pass after pass, strip after strip, the radar built a picture of the surface that transformed everything scientists thought they knew about moons in the outer solar system. The northern hemisphere was dotted with dark patches, dozens of them, some small, some enormous. When scientists analyzed the radar returns, the conclusion was inescapable. These were lakes. Bodies of standing liquid on the surface of a moon, not water, liquid methane and ethane, hydrocarbons that exist as gas on Earth but at Titan's temperatures, nearly 200 degrees below 0 Celsius, condense into liquid and pool on the surface just as water pools on ours. The lakes were not all the same size. Some were small, a few kilometers across. Others were vast. Kraken Mare, the largest, stretches roughly 1,170 kilometers from end to end. That is larger than the Caspian Sea on Earth. Ligeia Mare, the second largest, spans roughly 500 kilometers. These are not puddles, they are seas. Titan has seas, and it has coastlines. The radar images revealed irregular, complex shorelines where liquid met solid ground. Bays, inlets, peninsulas, flooded river mouths. The geometry was so Earth-like that if you stripped away the labels and showed someone a radar image of Titan's northern lake district beside a radar image of the lake country in northern Canada or Finland, many people would not be able to tell which was which. The rivers that Huygens had glimpsed during its descent were confirmed across the entire surface. Titan has an extensive network of channels, some dry, some apparently wet, that run for hundreds of kilometers across the landscape. They branch, they merge, they follow topography, they carve valleys. They do exactly what rivers do on Earth. They carry liquid from higher ground to lower ground and deposit it in basins where it collects as lakes and seas. And it rains. Titan has rain. Not constantly, not everywhere, but the evidence is overwhelming. Cassini observed cloud formations building, thickening, and dissipating over Titan's polar regions and occasionally over its equatorial zones. The Huygens probe measured methane humidity in the lower atmosphere that increased as it descended, reaching near saturation close to the surface. Scientists have modeled and observed evidence of methane rainstorms on Titan, downpours that may be infrequent but intense, capable of dumping large volumes of liquid methane onto the surface in short periods. The precipitation drives a cycle. Methane evaporates from the lakes and seas. It rises into the atmosphere. It condenses into clouds. It falls as rain. The rain flows across the surface, carving channels and filling depressions. The liquid collects in basins. It evaporates again. Evaporation, condensation, precipitation, runoff, collection. This is a hydrological cycle, not a water cycle, a methane cycle. But structurally, functionally, dynamically, it operates on the same principles as the water cycle on Earth. Titan has weather. Real weather, driven by the same thermodynamic processes that drive weather here. The parallels kept stacking. Cassini's radar revealed vast fields of longitudinal dunes stretching across Titan's equatorial regions. These dunes run roughly east to west for hundreds of kilometers, reaching heights of roughly 100 meters. Their shape and organization match the pattern of sand dunes found in the Namib Desert in Africa or the Arabian Peninsula on Earth. They form through the same mechanism. Wind blowing across a surface covered in loose particulate material, piling it into long parallel ridges aligned with the prevailing wind direction. On Earth, the particles are silicate sand grains. On Titan, the particles are something else entirely. But the process is the same. Wind, loose material, accumulation, dune formation. The physics does not care what the grains are made of. It only cares about size, density, wind speed, and supply. And on Titan, all four of those conditions are met, producing a dune landscape so visually similar to Earth's deserts that the comparison became a staple of every planetary science lecture for the next decade. Mountains were found as well. Not towering ranges, but ridges and highlands of water ice rising hundreds of meters above the surrounding terrain. Titan's crust is water ice, frozen so thoroughly at those temperatures that it behaves mechanically like rock on Earth. The mountains are ice. The bedrock is ice. The pebbles that Huygens photographed on the surface were ice. Everything structural on Titan that would be made of rock and mineral on Earth is made of water ice so cold it might as well be granite. And then there was the atmosphere itself, beyond just its composition. Cassini and ground-based observations revealed that Titan's atmosphere has a layered structure with a troposphere, stratosphere, mesosphere, and thermosphere. Earth's atmosphere has the same four layers, defined by the same alternating pattern of temperature increasing and decreasing with altitude. The scale heights are different. The temperatures are different. The chemistry is wildly different. But the architecture is the same. The atmospheric dynamics follow the same physics. Hadley cells circulate air from warmer regions to cooler ones. Seasonal changes in solar heating drive shifts in atmospheric circulation patterns. A polar vortex forms over the winter pole as stratospheric gases subside and accumulate. By the end of Cassini's 13-year mission at Saturn, which concluded in September 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere, the portrait of Titan had become the most unexpected result in the history of outer solar system exploration. Here was a moon orbiting a gas giant in the cold outer reaches of the solar system that had a thick nitrogen atmosphere with a surface pressure close to Earth's. It had a methane cycle that structurally mirrored Earth's water cycle. It had rain, rivers, lakes, and seas. It had coastlines, river deltas, and flooded valleys. It had dunes shaped by wind. It had mountains of ice. It had clouds, weather systems, and seasonal variation. It had atmospheric layers organized in the same sequence as Earth's own atmosphere. It had a surface where you could stand, look around, and see a landscape that your brain would immediately attempt to categorize as familiar. No other moon in the solar system does this, not one. Europa has a subsurface ocean, but its surface is a radiation-blasted sheet of cracked ice with no atmosphere to speak of. Enceladus vents water into space from its south pole, but it is a tiny world with no weather, no rain, no rivers. Ganymede is large but essentially airless. Io is a volcanic hellscape with sulfur dioxide, frost, and lava lakes. Triton has a thin atmosphere and nitrogen geysers, but nothing approaching the complexity of what Titan displays. Every other moon in the solar system is immediately, obviously alien. You look at them and your brain says, that is not Earth, that is something else. That is somewhere I do not recognize. Titan is different. Titan is the only moon where your brain hesitates, where the shapes and patterns and processes are so structurally similar to what you know from your own world that your instinct is to say, I recognize this, I know what this is. This looks like home. And that instinct is the most dangerous thing about Titan, because the resemblance is real. The structural parallels are not metaphors. They are not poetic comparisons made by enthusiastic science communicators. They are measured, documented, peer-reviewed physical facts. Titan genuinely has weather. It genuinely has a liquid cycle. It genuinely has an atmosphere dominated by nitrogen at a pressure close to sea level on Earth. These are not approximate similarities. They are precise functional analogues operating under the same physical laws, but the materials are wrong, the temperatures are wrong, the chemistry is wrong. Everything that makes Earth's versions of these processes friendly to life, supportive of biology, safe for a human body, is absent on Titan, replaced by something else. Something that keeps the shape of the familiar while filling it with substances and conditions that are hostile beyond anything most people can intuitively grasp. The rivers are not water. The rain is not water. The seas are not water. The dunes are not sand. The rocks are not rock. The air is not breathable. The temperature is not survivable. The chemistry is not life-supporting in any way that terrestrial biology would recognize. Every single feature that makes Titan look like Earth is built from ingredients that would kill you. This is the trap that Titan sets. It offers recognition. It presents shapes and processes that the human mind is wired to interpret as safe, as known, as home. And behind every one of those shapes is a reality so cold, so chemically alien, and so fundamentally incompatible with human life that the familiarity becomes something much worse than strangeness. A world that looks completely alien is just alien. Your brain processes it as foreign and moves on. A world that looks like home but is not. A world that triggers recognition and then violates it at every level of physical reality. That world occupies a different category entirely. It is not just hostile. It is uncanny. It is wrong in a way that feels personal because it is using the visual language of your own planet to describe conditions that could never support your existence. Scientists began calling Titan the most Earth-like body in the solar system. And they were right, in the narrow structural sense that no other world matches as many of Earth's surface processes as Titan does. But that phrase, Earth-like, carries an emotional weight that the science does not support. Earth-like sounds warm, it sounds promising, it sounds like a place you might want to go. The reality of Titan is the opposite of every one of those feelings, and the deeper you look, the worse it gets, because the parallels between Titan and Earth are not just structural, they extend into chemistry, into atmospheric history, into the kinds of organic complexity that scientists associate with the conditions that preceded life on our own planet billions of years ago. Titan does not just look like Earth on the surface. In some ways, it looks like young Earth, the version of our planet that existed before biology took hold. When the atmosphere was thick with nitrogen and methane, and the chemistry was assembling the first molecular building blocks of life in a world that had not yet learned how to be alive. That comparison has driven an entire branch of astrobiology research, and it raises a question that makes Titan even more unsettling than its frozen rivers and methane seas already suggest. If Titan mirrors the conditions of early Earth, then what is happening in those lakes? In that atmosphere? In the exotic chemistry that plays out on surfaces where hydrogen cyanide and hydrocarbons interact under conditions that no laboratory on Earth can perfectly replicate? The answer to that question requires looking past the familiar shapes and into the dark materials that fill them. It requires understanding what Titan's rain is actually made of, what its seas actually contain, and what happens when you take every comforting parallel between this moon and your home planet and examine it closely enough to see that the reflection in the mirror is not smiling back at you. It is doing something else. Entirely. Start with the air. That is the first thing that would kill you on Titan, and it is the first place where the Earth comparison begins to curdle. The atmosphere is nitrogen. 94% nitrogen. Earth's atmosphere is 78% nitrogen. So far, so familiar. You breathe nitrogen every second of your life. It makes up the bulk of every breath you have ever taken. Your lungs are full of it right now. On Titan, the nitrogen is there too. Structurally, the atmospheres of these two worlds share their dominant ingredient the way two recipes might share the same base flour. But flour is not a cake, and nitrogen is not an atmosphere. What matters is everything else mixed into it. On Earth, the remaining 21% of the atmosphere is oxygen. That single gas is the reason you are alive. It is the reason fire burns. It is the reason metal rusts, fruit rots, and every aerobic organism on the planet can extract energy from food. Oxygen is not a minor additive. It is the chemical foundation of terrestrial biology. Remove it, and every animal on Earth dies within minutes. On Titan, there is no free oxygen. None. Zero. The remaining fraction of the atmosphere, roughly 5 to 6% near the surface, is methane, not oxygen, methane. And above the methane, in the upper reaches of the atmosphere where ultraviolet radiation from the distant sun breaks molecules apart and reassembles them into new configurations, there is a stew of hydrocarbons and nitriles, so complex that chemists are still cataloging its full contents. Ethane, acetylene, propane, diacetylene, hydrogen cyanide, cyanoacetylene, cyanogen. These are not exotic trace compounds detectable only with the most sensitive instruments. They are bulk atmospheric constituents produced continuously by photochemistry in the upper atmosphere and settling downward through the haze layers in a slow, permanent rain of organic particles. Hydrogen cyanide deserves a moment of specific attention. On Earth, hydrogen cyanide is one of the most acutely toxic substances known. It kills by binding to the enzyme cytochrome C oxidase in mitochondria, shutting down cellular respiration at the molecular level. A few hundred parts per million in air is lethal to humans within minutes. On Titan, hydrogen cyanide is a routine atmospheric product. It is manufactured continuously by the interaction of solar ultraviolet light with nitrogen and methane in the upper atmosphere. It drifts downward. It accumulates on the surface. It participates in the chemistry of the lakes and the composition of the solid organic material coating the ground. It is not a contaminant on Titan. It is a feature. And this is where the atmosphere stops feeling like a cousin of Earth's and starts feeling like something designed by a chemist with no interest in keeping anything alive. The nitrogen gives you the structure, the methane gives you the weather, and the photochemistry gives you a toxic fog of hydrocarbon and nitrogen-bearing compounds that would be immediately lethal to any terrestrial organism and that coats every surface, fills every basin, and saturates every layer of the atmosphere from the ground to the edge of space. The haze itself is one of the most distinctive and disturbing features of Titan's atmosphere. When ultraviolet photons from the sun strike methane and nitrogen molecules in the upper atmosphere, they shatter them into reactive fragments. Those fragments recombine into increasingly complex organic molecules. The molecules cluster together, they grow. They form tiny solid particles called tholins, a word coined by Carl Sagan from the Greek word for muddy. These tholins are not a single compound. They are a heterogeneous mix of large, complex organic molecules with structures that researchers are still working to characterize fully. Laboratory simulations produce brown, sticky, tar-like material when the process is replicated on Earth. On Titan, these particles form continuously in the upper atmosphere and drift downward through hundreds of kilometers of air. They create the layered haze that gives Titan its opaque orange appearance from space. They are the reason no visible light from the sun reaches the surface in any useful quantity. They are the reason Titan's sky, from the ground, is not blue or black, but a deep brownish-orange twilight at all times. And they are the reason the surface of Titan is coated in a layer of organic sediment that has been accumulating for potentially billions of years. Some models estimate that the total depth of organic material deposited on Titan's surface over its history could be tens to hundreds of meters thick in places. An entire world slowly burying itself in its own atmospheric exhaust. Now, take the rain. We have established that Titan has a methane cycle, structurally analogous to Earth's water cycle. Evaporation, condensation, precipitation, runoff, collection. The process is real, the physics is identical, but the substance is not. Water, the liquid that drives Earth's weather, is one of the most extraordinary chemical compounds in existence. It is a polar molecule, meaning it carries an uneven charge distribution that gives it remarkable properties as a solvent. It dissolves salts, sugars, amino acids, and the vast majority of biological molecules. It remains liquid across a wide temperature range at Earth's surface pressure. It expands when it freezes, causing ice to float, which insulates liquid water beneath and prevents oceans from freezing solid. It has a high heat capacity that stabilizes global temperatures. It participates directly in the chemistry of life, serving as a medium, a reactant, and a structural component of biological molecules. Water is not just the stuff that falls from the sky. It is the operating fluid of terrestrial biology. Methane has almost none of these properties. It is a non-polar molecule. It is a poor solvent for the kinds of complex polar molecules that make up terrestrial biochemistry. It is liquid on Titan only because the temperature is so extraordinarily low, roughly -179 degrees Celsius, that even methane, a substance that exists as a gas at every naturally occurring temperature on Earth's surface, condenses into a clear, colorless liquid. Methane rain on Titan is not warm, it is not nurturing. It is not a medium that could support the kind of biochemistry that sustains life on Earth. It is a cryogenic hydrocarbon fluid falling from an orange sky at a temperature that would flash freeze any biological tissue on contact. The rain falls slowly. Titan's gravity is roughly 1/7 of Earth's, and the atmosphere is dense. Raindrops on Titan, modeled by scientists using fluid dynamics equations adapted for Titan's conditions, would be larger than Earth raindrops, roughly a centimeter across, and would fall at roughly 1.5 meters per second. On Earth, a raindrop of that size would fall at roughly 9 meters per second. On Titan, the rain drifts down through thick, cold air like slow-motion beads of liquefied natural gas descending through an orange fog. When that rain reaches the ground, it flows. It follows topography. It carves channels, and the channels it carves are visible in Cassini radar images and Huygens descent photographs as branching, dendritic networks that look strikingly like river systems on Earth. The shape is identical. The mechanism is identical. Liquid falling on a surface, collecting, flowing downhill, eroding softer material, depositing sediment in lower basins. The physics of fluvial erosion does not care whether the liquid is water or methane. It only cares about flow rate, viscosity, slope, and the mechanical properties of the surface material. But the surface material on Titan is not rock, it is water ice. Frozen to roughly -179 degrees Celsius, water ice at that temperature is mechanically indistinguishable from solid rock. The rivers of methane are carving valleys through ice bedrock that behaves mechanically like stone. And the sediment they carry, the particulate material washed downstream and deposited in deltas and lake basins, is not silicate sand. It is organic matter, tholin particles. Frozen fragments of the photochemical haze that rained down from the atmosphere and accumulated on the surface, then were picked up by methane rainfall and transported downstream. The river deltas on Titan are deltas of hydrocarbon sludge deposited into lakes of liquid methane and ethane, framed by valley walls of ice as hard as terrestrial bedrock. The lakes themselves are the most visually Earth-like feature on Titan and the most chemically alien. Kraken Mare, the largest, has an estimated area of roughly 400,000 square kilometers. For context, that approaches the size of the Black Sea on Earth. It is not a puddle. It is a genuine sea of liquid hydrocarbons, predominantly methane, with a significant fraction of ethane, and smaller amounts of dissolved nitrogen. The depth of Kraken Mare is not precisely known but is estimated to reach at least several hundred meters in some locations. The surface of these seas is remarkably calm. Cassini observations found that for most of the mission, the lakes and seas of Titan were almost perfectly smooth, showing virtually no evidence of waves. On Earth, any large body of liquid exposed to an atmosphere with wind develops surface waves within minutes. On Titan, the physical properties of liquid methane and the conditions near the surface conspire to suppress wave formation to an extraordinary degree. For most of the Cassini mission, the northern seas were in winter darkness, their surfaces locked in a stillness so complete that the radar return looked like a polished mirror. Later, as the northern hemisphere moved into summer and wind patterns began to shift, there was tentative evidence of slight surface roughening on some of the larger seas, the faintest suggestion that Titan's oceans might eventually stir. But the stillness was the dominant signal. Even the seas are quiet. Even the storms are slow. Everything on Titan operates at a pace that feels subdued, muffled, as if the cold has slowed the entire world into a thick, deliberate crawl. And the methane cycle carries another Earth-like inversion that Cassini documented over the course of its 13-year mission. On Earth, the distribution of water is shaped by seasons. Snow accumulates at the poles in winter, ice melts in summer, rainfall patterns shift with the monsoons. The geography of water on Earth is a living, breathing map that redraws itself every year as the planet's axial tilt changes the distribution of solar energy across the hemispheres. Titan does the same thing. But the mechanism is subtly and importantly different. Saturn's orbit around the Sun is not a perfect circle. It is an ellipse with enough eccentricity that Saturn is roughly 12% closer to the Sun during the southern hemisphere's summer than during the northern hemisphere's summer. This means Titan's southern summers are shorter but more intense. More solar energy reaches the surface per unit of time. Evaporation rates are higher. The weather is more violent. And the methane that evaporates from the south during these hot, short summers is transported northward through atmospheric circulation and deposited as rain in the cooler, longer northern winters. The result is a measurable asymmetry. Cassini found that the vast majority of Titan's lakes and seas are concentrated in the northern hemisphere. The south has far fewer standing bodies of liquid. This is not random geography. It is a direct consequence of the orbital mechanics of Saturn, shaping the methane cycle on a moon that orbits it. The methane is systematically pumped from south to north over timescales of tens of thousands of years, filling the northern basins while draining the southern ones. Earth's water is redistributed by seasons too, but the mechanism is different, and the asymmetry is far less extreme. Titan takes the concept of seasonal redistribution and amplifies it into a hemispheric scale pumping system that literally moves the moon's oceans from one pole to the other over geological time. This means that the geography you see on Titan today, the concentration of dark seas in the north and dry plains in the south, is not permanent. It is a snapshot of a cycle that is slowly, over thousands of Titan years, reversing itself. The southern hemisphere had seas once. It will have them again. The northern seas will evaporate, and the methane will migrate south. The coastlines that Cassini mapped are temporary coastlines. The rivers that feed the northern lakes will dry up, and new rivers will form in the south. The entire surface hydrology of Titan is a clock, ticking on a timescale set by the wobble of Saturn's orbit, redrawing the map of liquid and dry land with each cycle. On Earth, we call this kind of process familiar. We understand seasonal redistribution. We watch the snow come and go, the rivers swell and recede. But on Earth, the liquid is water. The cycle takes 1 year, and the redistribution is measured in meters of snowpack and centimeters of rainfall. On Titan, the liquid is methane. The cycle takes tens of thousands of Earth years, and the redistribution moves entire seas from one hemisphere to another. The concept is identical. The scale is alien. The substance is lethal. The inversion pattern holds. The dunes compound the wrongness. In the equatorial regions, Cassini's radar mapped vast sand seas of longitudinal dunes stretching for thousands of kilometers. Their shape and spacing match the physics of wind-blown dune formation on Earth precisely. But the sand is not sand. The particles that make up Titan's dunes are organic solids, likely a mix of tholins and other photochemical products that settled out of the atmosphere, accumulated on the surface, and were mobilized by equatorial winds into dune fields. You are looking at dunes made of something closer to soot or frozen tar than to the quartz grains that make up a beach on Earth. They are dark. They absorb radar, and they cover a significant fraction of Titan's equatorial surface, forming a belt of organic desert that wraps around the moon like a band of frozen industrial residue circling the waste of an icy world. Beneath the dunes, beneath the organic sediment, beneath the ice crust, there is yet another layer where the Earth-Titan inversion operates. In October 2024, a study revealed that methane gas is not confined to Titan's atmosphere and surface liquids. It is trapped within the icy crust itself, forming a distinct methane-rich layer that may extend up to roughly 10 kilometers thick. This methane clathrate crust, a zone where methane molecules are locked inside cages of water ice crystal, acts as an insulating blanket over the deeper ice shell. The implications are significant. On Earth, the crust is rock and mineral, warmed from below by radioactive decay and residual primordial heat, insulated from above by atmosphere and ocean. On Titan, the crust is water ice, and the insulating layer above the deeper shell is not air or water, but a thick zone of methane-infused ice that traps heat from tidal dissipation below. This methane crust warms the underlying ice shell, altering the thermal profile of the entire interior and affecting how the deeper slushy layers behave. It is another structural parallel to Earth, executed in alien materials. Earth has a warm crust insulated by atmosphere. Titan has a cold crust insulated by methane ice. The architecture serves the same function. The materials are from a different chemical universe. In October 2025, researchers at Chalmers University and NASA published a discovery that added another layer of alien chemistry to Titan's surface. They found that methane, ethane, and hydrogen cyanide, three of the most abundant compounds on and around Titan, can form stable co-crystals at Titan's surface temperature. Co-crystals are organized structures where two or more distinct chemical species arrange themselves into a shared crystal lattice. On Earth, polar molecules like hydrogen cyanide and non-polar molecules like methane and ethane do not mix in this way under normal conditions. The basic rule of chemistry, like dissolves like, says that polar and non-polar substances resist combining. On Titan, at -179 degrees Celsius, that rule breaks down. The substances mix. They form ordered crystalline structures that should not exist according to the chemistry you learn in a standard classroom. This means the surface of Titan is not just coated in organic gunk. It may be organized, at the molecular level, into exotic crystal structures that have no analog on Earth. The geology of Titan is not just ice and hydrocarbon sediment. It is a surface where the fundamental rules of chemical miscibility operate differently because the temperature is so far below anything that terrestrial chemistry normally encounters. The ground you would walk on is not just cold and alien. It is chemically impossible by the intuitions of room temperature chemistry. The minerals beneath your feet would be substances that could not exist on your home planet. The atmosphere contributed its own recent surprise. In May 2025, researchers at the University of Bristol published an analysis of 13 years of Cassini thermal infrared data, revealing that Titan's stratosphere does not rotate in line with its surface. The atmosphere tilts. It wobbles. It shifts orientation with the seasons, like a gyroscope whose axis drifts as the forces acting on it change. The thick, hazy atmosphere of Titan is not rigidly coupled to the moon beneath it. It slides, lags, and precesses on its own schedule, driven by the interaction between solar heating, Saturn's gravitational influence, and the internal dynamics of the atmospheric circulation itself. On Earth, atmospheric dynamics are complex but well mapped. The atmosphere broadly co-rotates with the surface, with deviations driven by differential heating and the Coriolis effect. On Titan, the disconnect between the atmosphere and the surface is more fundamental. The atmosphere super-rotates, meaning the winds at altitude move faster than the surface beneath them. This was known from Huygens' descent measurements. But the wobble adds a new dimension. The entire stratospheric tilt shifts over Titan's year, which lasts roughly 29.5 Earth years. The atmosphere is not just moving faster than the ground. It is pointing in a slightly different direction, and that direction changes as Saturn orbits the Sun. This discovery has direct practical implications for the Dragonfly mission. When the nuclear-powered rotorcraft descends through Titan's atmosphere after arriving in 2034, the winds it encounters will not simply be horizontal flows. They will carry the probe along a trajectory influenced by an atmosphere that wobbles seasonally relative to the surface below. The landing calculations must account for this atmospheric tilt. A world that already complicates every Earth comparison now turns out to have an atmosphere that does not even stay aligned with its own ground. And then there is the question of what lies beneath the surface. For years, one of the most exciting aspects of Titan was the hypothesis that a global subsurface ocean of liquid water might exist beneath its ice shell, similar to the suspected oceans beneath Europa and Enceladus. Cassini gravity measurements and observations of how Titan deformed under Saturn's tidal pull seemed to suggest that the interior was liquid enough to flex substantially. A global ocean would mean that Titan had not one but two liquid environments, hydrocarbon seas on the surface and a water ocean below the ice. The astrobiology implications were enormous. In December 2025, a team led by researchers at NASA's Jet Propulsion Laboratory published a study in Nature that significantly revised this picture. By reanalyzing Cassini Doppler data with a novel noise reduction technique, they detected a signature of strong energy dissipation deep inside Titan. The pattern they found was not consistent with a global ocean of liquid water sloshing beneath the ice. Instead, it pointed to something different, a thick, slushy interior. Layers of high-pressure ice mixed with pockets and pathways of liquid water, not a free ocean but a viscous, semi-solid matrix with isolated liquid reservoirs scattered through it. The lead researcher, Flavio Petrica, described the interior as more like Arctic sea ice or subsurface aquifers than an open ocean. The slush has low enough viscosity to allow Titan to flex under Saturn's tides, which explains the Cassini observations. But the liquid component is limited and dispersed, not a connected global sea. The pockets of meltwater may be as warm as 20 degrees Celsius in some locations near the rocky core, heated by tidal energy dissipation. These warm water pockets cycle nutrients from the rocky core upward through slushy high-pressure ice layers toward the solid ice shell at the surface. This finding changes the Titan story in a way that deepens rather than diminishes the moon's strangeness. A global subsurface ocean would have been an exciting but conceptually familiar feature, an underwater world hidden beneath ice, like a frozen version of Earth's own deep oceans. The slushy alternative is less dramatic, but more alien. Titan's interior is not a hidden sea. It is a thick, cold, semi-solid matrix of ice and brine, with scattered warm pockets that may or may not communicate with each other, buried under a crust that itself is buried under layers of frozen organic material deposited from the atmosphere. The interior of Titan is not just different from the surface, it is differently different. It resists analogy at every level, and this brings us to the most important inversion of all, the one that sits at the center of every comparison between Titan and Earth and makes the entire dark twin framing so powerful. On Earth, the familiar features, the weather, the rain, the rivers, the seas, are all connected to life. The water cycle is not just a physical process. It is the circulatory system of the biosphere. Rain feeds rivers that feed ecosystems. Evaporation from oceans drives atmospheric circulation that distributes heat and moisture across the planet. The chemistry of water enables the chemistry of biology. Every river, every cloud, every coastline on Earth exists within a web of living systems that depend on those features and are sustained by them. When you see rain on Earth, you are seeing life's infrastructure in motion. On Titan, the methane cycle has no such connection. The rain falls and nothing grows. The rivers flow and nothing drinks. The seas fill and nothing swims in them, at least nothing that any current observation can detect. The weather system operates with the same physics, the same thermodynamic elegance, the same beautiful structural logic as Earth's, but it runs in a void. It is a machine with no purpose. A circulatory system pumping fluid through a body that has no organs. The infrastructure of a living world, built in a place where the conditions for life, as we know it, do not exist. That absence is what transforms the resemblance from interesting to deeply unsettling. Titan does not just fail to support life. It performs an elaborate impersonation of a world that should support life and then does not. Every feature invites expectation. Every expectation is violated. The rain should be water, it is methane. The seas should be habitable. They are cryogenic hydrocarbon. The air should be breathable. It is laced with hydrogen cyanide. The surface should be geologically alive. It is ice, pretending to be rock, covered in tar, pretending to be soil, under a sky, pretending to be overcast, when it is actually filled with photochemical poison. The chemistry makes the comparison worse, not better. In 2025, a research team led by Antonin Affolter modeled what life on Titan could plausibly look like if it existed at all. They focused on the most basic possible metabolism, fermentation, the kind of primitive energy extraction that does not require oxygen or any other oxidant. Their conclusion was sobering. Even under the most generous assumptions, Titan's subsurface environment could support only a tiny total biomass, perhaps a few kilograms for the entire moon. The organic material is abundant, but the right kind of organic material, the kind that simple organisms could metabolize, is scarce. Titan has carbon everywhere. It has complexity everywhere. But it does not have the specific chemical pathways that biology needs to sustain itself in any meaningful quantity. Then, in July 2025, NASA researchers published a study showing that in Titan's hydrocarbon lakes, simple molecules called amphiphiles could theoretically self-organize into vesicles, tiny bubble-like structures that mimic the membranes of living cells. These vesicles would not be made of the lipids that form cell membranes on Earth. They would be made of nitrogen-bearing organic compounds, interacting with liquid hydrocarbons under conditions that are chemically alien to terrestrial biology. The process involves atmospheric molecules splashing into the lakes, carrying complex organics down from the photochemical haze, where they encounter conditions that may encourage self-assembly into cell-like compartments. This is not evidence of life. It is evidence that one of the preliminary structural steps toward life, the formation of enclosed compartments, might be physically possible under Titan conditions. It is a hint that Titan's chemistry is not just complex, but organizationally complex, capable of producing structures that echo the architecture of biology without necessarily leading to biology itself. And that might be the most disturbing finding of all. Titan is not just a world that looks like Earth on the outside. Its chemistry is producing molecular structures that look like the precursors of life. It is running a version of the same prebiotic chemistry that scientists believe operated on early Earth before the first living cell appeared. The shapes are there. The structural motifs are there. The organizational tendencies are there. But the temperature is wrong. The solvent is wrong. The energy budget is wrong. And the result, as far as any current evidence can determine, is a world that rehearses the opening act of life's story without ever reaching the first scene. Titan assembles the pieces. It arranges them on stage. It dims the lights and sets the atmosphere. And then the curtain does not rise. The show does not begin. The audience sits in the cold dark forever, watching a stage that is permanently set for a performance that will never start. Every new discovery about Titan deepens this pattern. The co-crystals on the surface organize molecules into structures. The vesicles in the lakes create cell-like compartments. The photochemistry in the atmosphere builds complexity, and none of it leads to life. None of it warms the surface. None of it lights the sky. None of it breaks the silence. The dark reflection is complete. Every Earth-like feature has been opened and examined, and inside each one is something profoundly, irreducibly wrong. Not wrong in the sense of broken, wrong in the sense of inverted. Titan has taken the blueprint of a living world and built it out of materials that preclude life. The architecture is flawless. The construction materials are fatal. But understanding the chemistry and the atmospheric composition from a datasheet is different from understanding what it would feel like, what the light would look like, what the silence would sound like, what the cold would do to you. The next step is to leave the instruments behind and stand, as much as imagination and data allow, on the surface of this world and look around. What a human body would experience on the ground of Titan is not just hostile. It is hostile in ways that specifically exploit the expectation of familiarity, because the landscape around you would look almost like somewhere you have been before, and the conditions would be more lethal than almost any environment the solar system has to offer. Close your eyes for a moment and picture arriving somewhere new on Earth. A coastline you have never visited. A valley you have only seen in photographs. The first thing that hits you is light, the color of the sky, the angle of the sun, the quality of the shadows on the ground. Then, sound. Wind across grass, or waves against rock, or the rustle of trees you cannot see yet. Then temperature on your skin. Then smell. Your body builds a model of where you are within seconds, and that model is almost always right, because your senses evolved on this planet and they know what its environments feel like. Now, open your eyes on Titan. The Huygens probe did this on January 14th, 2005. It did not have a human body, but it carried instruments that measured everything a human body would have felt: temperature, pressure, light levels, wind speed, surface hardness, atmospheric composition at every altitude, from the top of the atmosphere to the ground. From that data, and from 16 years of orbital measurements by Cassini, scientists have assembled a detailed reconstruction of what a human being would actually experience standing on the surface of this moon. Every number that follows comes from those measurements, or from physical models directly constrained by them. Start above the surface and work your way down. You enter Titan's atmosphere from above, falling through a region of sparse gas and ultraviolet haze at altitudes above 1,000 kilometers. The temperature up here is surprisingly high, roughly 150 to 200 Kelvin, heated by the absorption of solar ultraviolet energy by haze particles and gas molecules. As you descend, the temperature drops. You pass through the mesosphere, where temperatures reach their coldest values outside the surface, dipping as low as roughly 115 Kelvin at around 500 kilometers altitude. The air is still too thin to feel, but if your instruments are running, they are already detecting methane, hydrogen cyanide, acetylene, and dozens of other organic compounds mixed into the nitrogen. Below 500 kilometers, you enter the stratosphere. Here, the atmosphere thickens, the haze deepens, the orange color intensifies, and a strange thing begins to happen. The light from above, already dim because Saturn sits roughly 9.5 times farther from the Sun than Earth does, begins to scatter and diffuse through the aerosol layers until it loses all directionality. There are no sharp shadows in Titan's stratosphere. There is no identifiable point source of light. The illumination becomes a uniform orange glow, the same brightness in every direction, like being inside a sphere of tinted glass with a dim lamp somewhere outside it that you cannot locate. You descend further. At roughly 250 kilometers, you pass through the stratopores, where temperatures reach a local maximum of roughly 160 to 180 Kelvin due to heating from haze absorption. Below this, the temperature decreases again through the lower stratosphere. The haze is now so thick that your visibility would be measured in kilometers at best, and the world around you is a featureless orange murk. If you looked up, you would not see the sun. You would not see Saturn. You would not see stars. You would see nothing but a dim, directionless amber glow fading into deeper amber above you. At roughly 50 kilometers altitude, you cross the tropopause. Below this boundary, you enter the troposphere, the weather layer, the equivalent of the lowest portion of Earth's atmosphere where clouds form, rain falls, and wind interacts with the surface. The temperature here continues to drop as you descend, reaching the surface value of roughly 94 Kelvin, which translates to approximately minus 179 degrees Celsius or minus 290 degrees Fahrenheit. This is where the methane weather happens. Clouds of methane ice and liquid methane droplets can form in this layer, particularly near the poles and occasionally over equatorial regions. If you descend through a methane cloud deck, you would pass through a region of reduced visibility where tiny droplets of liquid natural gas condense on every surface, including you. The final few kilometers of descent are the strangest. The atmosphere below the cloud deck clears somewhat. Not to transparency, but to a murky translucency where you can see the ground approaching below you. And the ground does not look like what you would expect from a world this alien. It looks like terrain. Huygens photographed this during its descent. The images show a landscape of rolling highlands cut by dark drainage channels, transitioning into a flat, darker lowland plain. The contrast between light and dark terrain, the branching patterns of the channels, the smooth gradation of the lowland surface all conspire to produce an image that looks hauntingly like an aerial photograph of a dry riverbed on Earth, taken on an overcast winter afternoon. You reach the surface. Huygens hit the ground at roughly 4.5 meters per second, a gentle impact cushioned by the thick atmosphere. It sank a few centimeters into the surface material before coming to rest. The onboard instruments immediately recorded the surface conditions that a human body would be subjected to. The surface pressure is approximately 1,470 millibars. On Earth, sea level pressure is roughly 1,013 millibars. The difference is not dramatic, but it is physically real. You would feel it, not painfully, not dangerously, but perceptibly. The sensation would be comparable to standing at the bottom of a swimming pool roughly 4.5 meters deep, where the water pressure adds a firm, persistent squeeze to your chest and ears. Except, it is not water pressing on you. It is cold, dense nitrogen gas, laced with methane and organic aerosols. Every breath, if you could breathe, would be drawing in a thick atmosphere that weighs more per cubic meter than the air at sea level on Earth. The gravity is low. Titan's surface gravity is roughly 1.35 meters per second squared, about 14% of Earth's. This is lower than the Moon's gravity, which is roughly 16% of Earth's. On Titan, you would weigh approximately 1/7 of what you weigh at home. A person who weighs 80 kilograms on Earth would weigh the equivalent of roughly 11 kilograms on Titan. You could jump several meters into the air with a casual push. Running would feel like bounding in slow motion. And the thick atmosphere would provide actual aerodynamic lift. Scientists have calculated, and this is not a joke, that a human being wearing wing-like surfaces on their arms could achieve sustained flight on Titan by flapping. The air is that thick. The gravity is that low. The combination creates conditions where powered human flight without an engine is physically possible. On a world where stepping outside without protection would kill you in seconds, the temperature is where everything becomes lethal. Minus 179 degrees Celsius at the surface. To put this in perspective that the human body can process, Consider that the coldest temperature ever recorded on Earth's surface is -89.2 degrees Celsius, measured at the Soviet Vostok station in Antarctica on July 21, 1983. Titan's surface is 90 degrees colder than the coldest place on Earth. The coldest place on Earth would feel like a warm summer day compared to Titan's baseline. At -179 degrees Celsius, exposed human skin would not merely get frostbitten. The water in your cells would freeze solid within seconds. The crystallization would shatter cell membranes, destroying tissue at the molecular level. Your blood, which is mostly water, would begin to freeze, starting from the extremities. The proteins in your skin and muscles would denature as ice crystals disrupted their folded structures. Any exposed part of your body would effectively become a brittle solid, as rigid and as dead as the ice bedrock beneath your feet. The process would not be slow. At a temperature differential of roughly 216 degrees between your body and the surrounding air, heat would transfer out of any unprotected surface almost instantaneously. Titan would not freeze you the way a cold winter freezes you. It would freeze you the way liquid nitrogen freezes a flower. Completely, instantly, irreversibly. Now, look around. You are standing on a flat, dark plain. The surface beneath your feet is a mix of water ice and organic sediment. Huygens measured the surface temperature warming slightly after landing, which scientists interpreted as evidence that the probe's heat was vaporizing small amounts of liquid methane in the surface material. The ground is damp, not with water, with methane. The pebbles and cobbles scattered around you, rounded and smooth like river stones on Earth, are water ice. Frozen to a temperature where ice has a compressive strength comparable to granite. If you picked one up and struck it against a rock on Earth, it would behave like stone. It would not melt in your hand, because your hand would already be frozen solid. The sky is orange, not the orange of a sunset, which is warm and directional and fading towards something brighter. A flat, uniform, oppressive orange that extends from horizon to horizon without variation. There is no visible sun. There is no visible disk of light anywhere in the sky. The illumination is approximately 1,000th the brightness of a sunny day on Earth. That is dimmer than heavy overcast. It is comparable to the light levels experienced on Earth in the minutes after sunset, the deep twilight period when colors begin to drain from the landscape and everything takes on a muted, monochromatic quality. On Titan, that twilight never ends. There is no sunrise coming. There is no brighter part of the sky to look toward. The entire dome above you is a uniform dim orange, and it will remain exactly that brightness for approximately 8 Earth days before Titan's rotation carries you into the night hemisphere, where the sky becomes simply black. That transition deserves attention because it is unlike anything experienced on any other world with an atmosphere. Titan is tidally locked to Saturn, meaning it rotates once on its axis for every orbit it completes around the planet. One full Titan day, from noon to noon, takes approximately 15.95 Earth days. That means roughly 8 Earth days of continuous dim orange twilight, followed by roughly 8 Earth days of darkness. There is no rapid sunrise and sunset cycle. There is no morning. There is no evening in the way you understand those concepts. The light fades over the course of hours as Titan's slow rotation carries your location past the terminator, the boundary between the illuminated and dark hemispheres. The transition is not dramatic. The sky, already dim and featureless, simply becomes dimmer. The orange darkens to a deep burnt umber, then to brown, then to nothing. At no point do stars appear. At no point does Saturn become visible. The haze remains opaque in all conditions. Day and night on Titan are the difference between dim orange murk and total blackness. And the cycle takes more than 2 Earth weeks to complete. During the Titan night, the temperature drops slightly, but not dramatically. The thick atmosphere acts as a thermal buffer, retaining heat through its greenhouse effect, even when the feeble solar input disappears. The difference between day and night surface temperatures is only a few Kelvin. The cold is so deep and so constant that the absence of the sun barely registers as a thermal event. You are not transitioning between warm and cool. You are transitioning between frozen and fractionally more frozen. Sound would behave differently on Titan than on any world you have experienced. The thick atmosphere and low temperature change the speed of sound significantly. On Earth, sound travels at roughly 343 meters per second in air at room temperature. On Titan, the speed of sound is approximately 200 meters per second. Sounds would arrive more slowly. More importantly, the denser atmosphere transmits sound more efficiently over distance. Quiet sounds would carry further. The acoustic environment would feel muffled in pitch, but strangely amplified in range, as if the entire world was speaking in a lower register but whispering directly into your ear. If there were any sound at all. Because on the surface, apart from the occasional gust of wind at typically less than 1 meter per second, there may be nothing to hear. No insects, no birds, no water flowing, no biological noise of any kind. A silence so complete that the only sound would be the faint hiss of your own equipment and the subtle pressure of atmosphere against your suit. In the distance, if visibility permits, you might see the edge of a methane sea. Kraken Mare, the largest body of liquid on Titan, has been mapped by Cassini radar to a length of roughly 1,170 kilometers. Its coastline is complex, irregular, carved with bays and inlets and partially submerged river channels that empty into the basin. If you walked to its shore, you would see a liquid surface so calm and so flat that it would look like a dark mirror set into the ice. The liquid is clear or slightly tinted. At Titan's surface temperature, liquid methane has a refractive index and transparency roughly comparable to gasoline. It is not opaque. If the sea were shallow enough and the light sufficient, you might see the bottom. You might see rounded pebbles of ice beneath a layer of transparent cryogenic hydrocarbon. The physical experience of touching the liquid, if your suit allowed it, would be alien in ways that go beyond temperature. Liquid methane at Titan conditions has a density of roughly 450 kilograms per cubic meter, less than half the density of water. A human body, even in a spacesuit, would not float in it. You would sink. The buoyancy that water provides on Earth, the familiar sensation of being supported by a liquid that is denser than your body, would not apply. Wading into Kraken Mare would be like wading into a fluid that offers almost no resistance and almost no support. A liquid so light that it feels closer to walking through cold air than through water. The thermal shock would be the more immediate problem. Liquid methane at minus 179 degrees Celsius coming into contact with a warm surface would boil violently. Your suit, your gloves, any warm object touching the liquid would produce a furious eruption of methane gas as the heat transferred from the warm object vaporized the surrounding liquid. You would be surrounded by a churning bubble of methane vapor, blinding your vision and creating local turbulence in an otherwise perfectly still sea. The interaction between a warm human body and Titan's cryogenic ocean would be explosive in slow motion, a thermal confrontation between two temperature regimes separated by more than 200 degrees. There would be no waves, or nearly none. The combination of low wind speeds, low surface tension, and high atmospheric density suppresses wave formation on Titan's seas to an extraordinary degree. The surface of Kraken Mare may ripple occasionally, particularly as the northern hemisphere moves into summer and winds strengthen slightly, but for most of Titan's long year, the seas are glass smooth. Standing at the shore of Kraken Mare would be like standing at the edge of a perfectly still pond at dusk, except the pond is the size of an inland sea, the liquid is methane, the shore is ice, and the temperature is cold enough to turn every molecule of water in your body into a solid crystal. Walk inland from the coast, and you enter different terrain depending on your latitude. In the equatorial regions, the landscape is dominated by the great dune fields. These longitudinal dunes stretch for hundreds of kilometers in parallel ridges, roughly 1 to 2 kilometers apart, reaching heights of approximately 100 meters. Walking through them would be an exercise in repetition, ridge after ridge of dark organic particulate material separated by flat interdune corridors. The surface underfoot would be loose, granular, composed of particles roughly the size of coarse sand but made of frozen organic compounds, tholin material, and possibly acetylene ice grains that settled from the atmosphere and were worked by wind into their current formations. The dunes would not feel like a terrestrial desert, despite looking like one. The gravity is too low. Each step would carry you further and higher than you expect. The fine organic particles kicked up by your passage would hang in the thick air longer than sand hangs in Earth's atmosphere, drifting slowly back to the surface in the weak gravity, like dark snowflakes settling through syrup. The wind that shaped these dunes into their current form is gentle by Earth standards, typically less than 1 meter per second near the surface, but the dense atmosphere means that even slow winds carry significant momentum. The force that a 1 meter per second wind applies to a surface on Titan is comparable to the force applied by a considerably faster wind on Earth, because the air itself is so much denser. The dunes were built by winds that would barely ruffle your hair on Earth, but that push heavy nitrogen gas across a low-gravity surface with enough force to mobilize particles and pile them into continent-spanning ridges. The weather would come slowly and violently. Titan's methane storms are infrequent but intense. Models suggest that major precipitation events may be separated by decades or even centuries at some latitudes. When they come hard. Simulations of Titan's methane rainstorms produce downpours that can deposit centimeters of liquid methane on the surface in a matter of hours. This rainfall runs off the frozen organic surface quickly, generating flash floods that carve the channels and valley networks visible in Cassini radar data. The floods are not gentle. Methane has a lower viscosity than water, and Titan's low gravity means that fluid dynamics on the surface operate differently. But the volume of liquid mobilized during a major rain event can produce rapid erosion and channel modification. Between storms, the surface is quiet. The equatorial dune fields stretch under the dim orange sky in long parallel ridges of organic sediment. The polar lake districts sit glassy and still under their perpetual haze ceiling. The mid-latitude plains, coated in organic material and ice fragments, experience almost no weather at all for years or decades at a time. Titan is a world of long, silent pauses, punctuated by brief, intense episodes of methane violence. The rhythm is nothing like Earth's daily weather cycle. It is closer to the rhythm of geological events, slow enough that a human standing on the surface might wait an entire lifetime without seeing rain. There is another presence on this world that no human visitor could see, but that permeates everything. Titan orbits Saturn. It is tidally locked, meaning the same hemisphere always faces the planet. From the sub-Saturnian point on Titan's surface, Saturn would dominate the sky, hanging permanently above the horizon, with an apparent diameter roughly 11 times larger than the Moon appears from Earth. But you would never see it. The haze is too thick, the atmosphere is too opaque. Saturn is up there, enormous, ringed, gravitationally dominant, tugging on Titan's interior with tidal forces that generate internal heat and drive the slushy dynamics below the ice shell. And you cannot see it. You know it is there because the tides tell you. Titan's surface deforms measurably under Saturn's pull, rising and falling by roughly 10 meters over each orbital period. The ground itself breathes, flexing under the gravitational grip of a planet you cannot see through the permanent orange murk above you. And in 2034, if everything goes according to the current schedule, something from Earth will descend through that murk and touch this surface for the second time. The Dragonfly mission, now in active integration and testing at the Johns Hopkins Applied Physics Laboratory as of March 2026, is a car-sized nuclear-powered rotorcraft designed to fly through Titan's thick atmosphere using 8 rotors, landing at multiple locations across the Moon's surface to analyze chemistry, geology, and atmospheric conditions. It will launch on a SpaceX Falcon Heavy rocket in July 2028 and arrive at Titan after a 6-year cruise. Dragonfly will land initially in the equatorial dune fields near a region called Shangri-La, then fly in a series of hops, each covering up to roughly 8 kilometers, toward the Selk impact crater, a feature roughly 90 kilometers in diameter, where scientists believe liquid water from a transient melt pool may once have mixed with the organic material on Titan's surface. That mixing zone is one of the most astrobiologically significant locations in the outer solar system, and the journey between those two sites is itself a traverse across some of the most geologically varied terrain on the Moon. The route from Shangri-La to Selk covers roughly 175 kilometers. It begins in the heart of the equatorial dune sea, where Dragonfly will spend its first flights sampling the organic composition of the dune material and interdune corridors. The early hops will cross ridge after dark ridge of wind-blown organic sediment, each flight carrying the rotorcraft over a landscape that from the air would look remarkably like a terrestrial sand sea photographed through an amber filter. The interdune corridors are flatter and may expose the underlying ice substrate, giving Dragonfly its first opportunity to compare the composition of wind-deposited organic material with the water-ice bedrock beneath it. As the mission progresses northward and eastward towards Selk, the terrain changes. The dunes thin and eventually give way to broader, flatter plains where the organic sediment layer is thinner and the ice substrate is more exposed. Cassini radar images of this transitional zone show a patchwork of bright and dark terrain with scattered drainage features and what may be remnants of ancient shorelines or flow margins from past methane flooding events. The geology here records a more complex history than the simple wind deposition story of the dune fields. This is terrain shaped by multiple processes: wind, liquid flow, possible cryovolcanic resurfacing, and the gradual accumulation and reworking of atmospheric fallout over geological timescales. As Dragonfly approaches Selk crater, the terrain begins to rise. The crater's degraded rim, eroded and softened by billions of years of exposure to Titan's atmosphere and occasional methane precipitation, stands only modestly above the surrounding plain. But the crater floor itself is the scientific prize. Impact models suggest that the energy released when the original impactor struck Titan's ice crust would have melted a volume of water ice sufficient to create a transient lake of liquid water covering the crater floor. That melt pool would have been warm by Titan standards, possibly above the freezing point of water for centuries to millennia, depending on the size and energy of the impact. During that window, liquid water would have interacted directly with the organic material on and in Titan's surface, creating a natural reactor where water-based chemistry and Titan's abundant carbon compounds mixed under conditions that are rare or unique on this moon. The floor of Selk crater today is cold and frozen, like everything else on Titan. But what happened during the transition from warm melt pool to frozen surface is itself a critical part of the story, and it is covered by a well-understood physical process that makes Selk even more scientifically valuable than the melt pool alone would suggest. When a body of liquid water freezes slowly, it does not solidify uniformly. The freezing front advances inward from the edges and surface, and as it does, it excludes dissolved solutes from the growing ice crystal lattice. Salts, organic molecules, mineral ions, anything dissolved in the water gets pushed ahead of the advancing ice into the remaining liquid. The effect is called freeze concentration, and it means that as the melt pool shrank over centuries, the liquid that remained became progressively more concentrated. Dissolved organic compounds that were dilute in the original warm pool would have been forced into smaller and smaller volumes of remaining liquid, packed together at densities orders of magnitude higher than the starting conditions. On Earth, freeze concentration is not just a physical curiosity. It is an experimentally demonstrated driver of prebiotic chemistry. Laboratory studies have shown that when dilute solutions of nucleotides are subjected to freeze-thaw cycling or slow directional freezing, the concentration effect promotes the formation of RNA-like polymers and peptide bonds that would not form in dilute solution at the same temperature. The freezing process itself acts as a chemical catalyst, not by adding energy, but by forcing reactants into close enough proximity that reactions become statistically inevitable. If the same mechanism operated at Selk crater, and there is no physical reason it would not, then the most chemically interesting products of the water-organic interaction would not be distributed evenly across the crater floor. They would be concentrated in specific zones corresponding to the last pockets of liquid to freeze. The eutectic remnants, where concentration effects were strongest, and where the molecular complexity had the greatest opportunity to ratchet upward before the cold finally locked everything in place. These zones would be small, isolated, and potentially rich in exactly the kinds of molecular structures that Dragonfly's mass spectrometer is designed to detect. Whatever chemical products were created during the melt pool era are now locked in ice and organic sediment, preserved by the deep cold that has held the surface in stasis since the water refroze. Dragonfly will sample this material directly, using its mass spectrometer to search for molecular signatures that indicate whether the water-organic interaction produced anything beyond what dry photochemistry alone can generate. The question is specific and profound. Did warm water touching Titan's organics create amino acids, nucleobases, or other molecular building blocks of life? Or did the interaction produce only the same kinds of complex but biologically irrelevant compounds that form in the atmosphere? Dragonfly will carry a mass spectrometer capable of analyzing the molecular composition of surface materials in detail. It will carry a gamma-ray and neutron spectrometer to map elemental abundances in the surface and subsurface. It will carry meteorological sensors to measure wind, pressure, temperature, and humidity at the surface. It will carry cameras to photograph the terrain from the air and from the ground. And it will carry a seismometer to listen for vibrations within Titan's ice shell, potentially detecting the tidal flexing caused by Saturn and mapping the internal structure of the Moon from the surface. The mission is designed to last roughly 3 Earth years on Titan's surface, during which time the rotorcraft will visit dozens of locations. It will fly through the thick atmosphere, powered by a multi-mission radioisotope thermoelectric generator that converts heat from decaying plutonium-238 into electricity, charging its batteries during the roughly 8 Earth day Titan night and flying during the dim Titan day. The rotors will bite into atmosphere denser than Earth's with gravity weaker than the Moon's, giving Dragonfly a flight envelope that is, paradoxically, easier to operate in than any aerial environment on Earth. Dense air and low gravity make flight almost absurdly efficient. Dragonfly can travel farther per flight than any surface mission in solar system history, covering distances that rovers on Mars would take months to achieve. But the engineering challenges are staggering. Everything on Dragonfly must operate at -179 degrees Celsius. The electronics, the motors, the structural materials, the sampling mechanisms, all must function in a thermal environment that would render most terrestrial hardware brittle and non-functional. The foam insulation that wraps the lander has been tested in a dedicated Titan simulation chamber at the Applied Physics Laboratory, subjected to the exact temperature and pressure conditions it will encounter on the surface. The flight radios, the mass spectrometer components, the rotor assemblies have all been through testing campaigns designed to simulate not just the cold, but the specific combination of cold, dense atmosphere, and low gravity that makes Titan unlike any other destination in the solar system. When Dragonfly touches down at Shangri-La in 2034, it will encounter the same conditions that Huygens measured nearly 30 years earlier, the same dim orange sky, the same thick, cold atmosphere, the same frozen surface of ice and organic sediment. But it will be able to do something Huygens could not. It will be able to move. It will fly from dune field to impact crater, sampling different geological contexts, comparing equatorial organic deserts with regions where transient water may have touched the surface. It will piece together the chemical history of a world that runs the prebiotic chemistry playbook from beginning to almost middle and then appears to stop. The data Dragonfly returns will answer questions that have haunted planetary science, since Cassini's first radar pass revealed lakes on a moon. How complex are the organics on Titan's surface? Do the tholins contain amino acid precursors? Has the transient water in impact melt pools catalyzed any molecular organization beyond what photochemistry alone can produce? Is there any chemical signature on Titan's surface that looks like it was influenced by processes that, on Earth, are associated with biology? Nobody expects Dragonfly to find life. The scientific community is careful and measured on that point. What Dragonfly is designed to find is the chemistry that precedes life, the molecular steps that lead toward biological complexity, frozen in time, on a world where the temperature is too low for those steps to continue to their conclusion. Titan may be a natural laboratory where prebiotic chemistry is preserved at a stage that Earth blew past 4 billion years ago, when the temperature was right and the water was liquid and the reactions kept going. Titan may show us what our own planet looked like before life began, captured in ice and methane, like a photograph of an ancestor, too ancient to have left any other record. And that is what makes standing on Titan, even in imagination, so profoundly disturbing. You are not standing on a dead world. A dead world implies something that was once alive or that had the potential and lost it. You are standing on a world that is performing every physical motion associated with life, weather, cycles, chemistry, molecular organization, and doing it in a context that cannot complete the process. The machinery runs, the engine turns over, the ignition sequence begins, and then it stalls, permanently, indefinitely. For billions of years. The surface of Titan is the surface of a world caught in an eternal almost. And the cold that holds it there is not going anywhere. Not in 1,000,000 years. Not in 1,000,000,000. The sun will grow brighter as it ages, but not enough to warm Titan above the threshold for liquid water on any timescale that matters for the current era of the solar system. The methane cycle will continue. The haze will continue to rain down organic particles. The seas will sit calm and dark under their perpetual orange ceiling, and the chemistry will continue to assemble complexity that goes nowhere. What that means. What it says about the nature of worlds that look like ours but are not, is the question that Titan ultimately forces us to answer. There are moons in this solar system that will kill you faster than Titan. There are moons that are more visually violent, more immediately dramatic, more obviously hostile to anything made of organic tissue and warm blood. If you ranked the moons of the solar system by sheer physical danger, Titan would not sit at the top, and that is precisely why it is the scariest one. Consider the competition. Io, the innermost of Jupiter's 4 large moons, is the most volcanically active body in the solar system. Its surface is a hellscape of erupting lava fountains, sulfur dioxide frost, and volcanic plumes that shoot material hundreds of kilometers into space. Tidal forces from Jupiter flex Io's interior so violently that the entire moon is essentially being kneaded like dough by gravity, generating enough internal heat to drive continuous volcanic resurfacing. Nothing about Io looks safe. Nothing about Io looks familiar. Nothing about Io tricks your brain into thinking you recognize it. You look at Io, and your instinct says danger immediately, without hesitation, without any need for explanation. Io advertises its hostility. It wears it on its sulfur-stained surface like a warning label. Europa, another of Jupiter's large moons, sits in one of the most intense radiation environments in the solar system. Jupiter's magnetosphere accelerates charged particles to enormous energies, and Europa orbits directly through the densest regions of those radiation belts. The surface radiation dose on Europa is approximately 540 rem per day. For comparison, a lethal dose for a human being is roughly 400 rem accumulated over a short period. Standing unshielded on Europa's surface would deliver a fatal radiation dose in less than a single Earth day. The surface is ice, cracked and fractured, covering a suspected ocean of liquid salt water that may be one of the most promising environments for extraterrestrial life in the solar system. But nothing about Europa's surface feels familiar. It is a barren, radiation-scoured ice sheet under a black sky with Jupiter looming enormous overhead. Your brain does not hesitate. It says, foreign. It says, alien. It says, not here. Enceladus, a tiny moon of Saturn barely 500 kilometers across, vents enormous plumes of water vapor and ice particles from fractures near its south pole. The jets contain organic molecules, silica nanoparticles, and molecular hydrogen, all signatures consistent with hydrothermal activity on the floor of a subsurface ocean. Enceladus may be one of the most habitable environments beyond Earth, but it is a small, bright, obviously icy world that looks nothing like any place you have ever visited. There is no atmosphere. There is no weather. There are no rivers, no coastlines, no landscapes that trigger any form of terrestrial recognition. Enceladus is interesting. It is scientifically extraordinary. It is not uncanny. Triton, Neptune's largest moon, has geysers of nitrogen gas, a thin atmosphere, and a surface temperature of roughly -235 degrees Celsius, making it one of the coldest known surfaces in the solar system. It is almost certainly a captured Kuiper Belt object, a wanderer from the outer reaches of the solar system that Neptune's gravity ensnared. Triton is strange, but it is straightforwardly strange. Nothing about it mimics Earth. Nothing about it creates the cognitive dissonance that Titan produces. And that is the distinction. Every other dangerous moon in the solar system is obviously dangerous. Visually, structurally, intuitively, they announce what they are. They look like hostile alien worlds because they are hostile alien worlds. Your brain has no trouble classifying them. They go into the mental category marked foreign, and they stay there. Titan refuses to stay in that category. Titan sits in the space between familiar and alien, between recognized and wrong, between this looks like home and this will kill you, and it occupies that space more completely than any other world ever discovered. That is what makes it uniquely disturbing, not the cold, not the methane, not the hydrogen cyanide. The fact that your brain keeps trying to make it Earth and it keeps failing. There is a concept in robotics and animation called the uncanny valley. It describes the psychological phenomenon where a humanoid figure that is almost but not quite realistic produces a stronger feeling of unease than a figure that is obviously artificial. A cartoon character does not disturb you because it is clearly not human. A perfect replica would not disturb you because it would be indistinguishable from a real person. But something in between, something that gets most of the details right but misses a few critical ones, something that looks close enough to trigger your facial recognition systems but wrong enough to set off your threat detection, that produces a deep, instinctive discomfort that is disproportionate to the objective level of difference. Titan is an uncanny valley for planets. It has enough Earth-like features to trigger recognition: atmosphere, weather, rain, rivers, lakes, seas, coastlines, dunes, seasons, clouds. A nitrogen-dominated atmosphere at a pressure you could physically tolerate. A hydrological cycle that obeys the same thermodynamic logic as the one outside your window. These are not minor similarities. They are the fundamental structural elements of a habitable world, present and functioning on a moon 1.5 billion kilometers from the sun. But every detail is wrong. The temperature is 200 degrees too cold. The liquid is the wrong chemical. The air is missing the one gas you need to survive. The ground is made of frozen water pretending to be stone. The sediment is organic poison pretending to be soil. The sky is a permanent orange twilight with no visible sun, no stars, no horizon break. The weather runs on methane. The chemistry produces hydrogen cyanide as a routine byproduct. The interior is slush, not ocean. The surface is coated in billions of years of photochemical tar. Each of those details individually would be unremarkable on a world that did not look like Earth. Minus 179 degrees on a barren ice moon with no atmosphere. Expected. Methane liquid on a frozen outer solar system body. Interesting, but not unsettling. Hydrogen cyanide in a thin, wispy atmospheric trace. A chemical curiosity. But on Titan, each of those details is embedded inside a structural framework that looks like your home planet. They are hidden inside the familiar, like finding a machine behind a face. The wrongness is not on the surface, it is under the surface, wrapped in a disguise of rivers and rain and coastlines that your mind wants to trust. This is why scientists have struggled for decades to describe Titan without either overstating the Earth comparison or understating the alienness. The phrase, most Earth-like body in the solar system, is technically accurate and profoundly misleading at the same time. It is accurate because no other world matches as many of Earth's active surface processes. It is misleading because the phrase suggests kinship, suggests warmth, suggests a world you might visit, live on, recognize as a distant cousin. Titan is not a cousin. It is a reflection in a mirror that has been built from different materials, assembled in the dark, and cooled to a temperature where every familiar shape becomes a shell containing something fundamentally incompatible with your existence. The most recent scientific findings have only deepened the inversion. In February 2026, a study led by SETI Institute scientist Mati Jachuk proposed that Titan itself may have formed through catastrophic violence. Computer simulations suggested that Saturn once had an additional large moon whose orbit became gravitationally unstable. In the most likely scenario from those simulations, the extra moon collided with a proto-Titan, and the two bodies merged in an impact so energetic that it reshaped both objects entirely. The Titan we see today, with its thick atmosphere and complex chemistry and eerily Earth-like surface, may be the product of a collision between two older moons that were individually unremarkable. A world forged in destruction, an Earth-like facade built on a foundation of ancient violence. This matters for the dark twin framing because it means that even Titan's origin story is an inversion of Earth's. Earth's moon was created by a giant impact roughly 4.5 billion years ago when a Mars-sized body called Theia struck the young Earth. That collision created the moon, helped establish Earth's axial tilt, and contributed to the conditions that made plate tectonics and climate stability possible. The Theia impact, for all its violence, was a constructive catastrophe. It helped make Earth habitable. Titan's proposed formation collision did the opposite. It created a body large enough to hold a thick atmosphere, complex enough to develop a methane cycle and photochemical haze production, and Earth-like enough in structure to fool your pattern recognition into seeing a habitable world. But the result of that violence was not habitability. It was the construction of the most elaborate, uninhabitable mimic in the solar system. Both Earth and Titan were born in fire. Earth's fire made life possible. Titan's fire made a world that performs the theater of life without ever hosting the substance. There is something that Titan teaches about the nature of habitability that no other world in the solar system can teach as clearly. And it is a lesson that cuts deeper than any individual fact about methane rain or hydrogen cyanide. Habitability is not a checklist. For decades, the search for habitable worlds beyond Earth operated on a model that treated habitability as a set of boxes to tick. Does the world have an atmosphere? Check. Does it have liquid on the surface? Check. Does it have a cycle that moves that liquid between surface and atmosphere? Check. Does it have weather? Check. Does it have complex chemistry? Check. Titan checks every one of those boxes. And it is not habitable. Not for life as we know it, not for biology based on water and carbon in the configurations that terrestrial organisms use. Titan demonstrates that you can have every structural prerequisite for a living world and still have a world that is fundamentally dead. The missing ingredient is not structural, it is thermal, it is chemical. It is the specific combination of a solvent that supports biochemistry, an energy source that drives metabolism, and a temperature range that allows the molecular interactions necessary for self-replicating chemistry to occur at rates fast enough to outpace degradation. Earth has that combination. Titan does not. And the gap between having the structure and having the chemistry is the gap between a world that is alive and a world that merely looks alive. This realization has implications that extend far beyond Titan. As astronomers discover more and more exoplanets, as the James Webb Space Telescope and future missions like the Habitable Worlds Observatory begin to analyze the atmospheres of rocky worlds around other stars, the temptation will be to treat atmospheric detection as a proxy for habitability. A planet with nitrogen and methane in its atmosphere, with evidence of a liquid cycle, with clouds and weather, will be immediately flagged as a candidate for life. Titan is the cautionary tale. Titan says that the shapes alone are not enough, that a world can perform every physical motion associated with a biosphere and still be a frozen, toxic, lightless wasteland where the chemistry of life cannot gain a foothold. Every future detection of an Earth-like atmosphere on a distant exoplanet will have to contend with the Titan problem. Is this world genuinely habitable, or is it another dark twin? Does the nitrogen atmosphere contain oxygen, or does it contain methane and hydrogen cyanide? Are the surface liquids water, or are they cryogenic hydrocarbons? Is the weather cycle supporting a biosphere, or is it running on autopilot in a world where the temperature precludes biology? Titan teaches us that the universe can build worlds that look right from a distance and are utterly wrong up close. It teaches us that resemblance is not equivalence. And it teaches us that the emotional response, triggered by seeing rivers and rain and coastlines on another world, must be treated with extreme caution, because those features can exist without any of the warmth, chemistry, or biological potential that we unconsciously associate with them. There is a deeper philosophical weight to Titan that scientists rarely articulate in formal papers, but that pervades the informal conversations of planetary researchers who have spent their careers studying this moon. It is the weight of recognition without connection. The sense that you are looking at a world that has done everything structurally possible to resemble yours and has still ended up somewhere completely different. Titan is not trying to be Earth. It is not a failed Earth. It is not a broken Earth. It is a world that followed different initial conditions through the same physical laws and arrived at a result that maps onto Earth's geography while diverging from Earth's chemistry at every molecular level. That divergence is what transforms the resemblance from fascinating to unsettling, because it reveals something about the universe that is easy to understand intellectually but difficult to absorb emotionally. The universe does not care about the distinction between habitable and uninhabitable. It does not reserve weather for living worlds and deny it to dead ones. It does not restrict rain to planets where rain supports biology. It does not limit coastlines to shores where organisms crawl out of the water and begin the long process of colonizing dry land. The physical processes that make Earth feel like home, that make it recognizable, that make it ours, are not special. They are generic. They are the default behavior of fluids and gases under gravity in the presence of an energy gradient. They occur wherever the conditions allow, regardless of whether the result is a garden or a graveyard. Titan is the proof. The universe built an Earth-like world in the outer solar system and filled it with methane and hydrogen cyanide and temperatures that would kill every organism on our planet. It gave that world rain and rivers and seas and an atmosphere you could almost breathe. And then it set the thermostat to -179 degrees and walked away. The result is a place that looks like it should be alive and is not. A place that resembles home from every angle except the ones that matter. And that brings us to the final reason why Titan is the scariest moon in the solar system. It is not the cold. Cold is just a number. It is not the methane. Methane is just a molecule. It is not the hydrogen cyanide or the organic haze or the perpetual twilight. Each of those features is frightening in isolation, but in isolation they are comprehensible. You can process them the way you process any hostile environment. You note the danger, you acknowledge it, you move on. What you cannot easily process is the combination, the totality, the experience of looking at a world that has assembled every visual element of habitability and embedded within it a chemical reality that negates all of it. Titan is scary because it occupies a psychological space that no other world occupies. It is close enough to home to feel personal, and far enough from home to feel like a betrayal. It is Earth reflected in a dark mirror, every feature preserved in shape but inverted in substance. The rivers run with liquefied natural gas. The rain is cryogenic hydrocarbon. The beaches are frozen water harder than granite. The sand is organic soot. The air is poisonous. The sky is a permanent dim orange that never brightens, never clears, never shows you a star or a sun or a glimpse of the universe beyond the haze. The ground flexes beneath you under the pull of a planet you cannot see. And the entire world is wrapped in a silence so deep and so permanent that the only things that have ever broken it are a single European space probe in 2005 and, if everything goes according to plan, a nuclear-powered American drone that will arrive 29 years later. Between those two visits, Titan will do what it has done for billions of years. The methane will evaporate from the seas. It will rise into the cold, thick atmosphere. It will condense into clouds. It will fall as rain. The rain will carve channels through ice bedrock and wash organic sediment into dark basins. The haze will continue to form in the upper atmosphere, particle by particle, settling downward through hundreds of kilometers of orange murk to coat the surface in another thin layer of photochemical residue. The dunes will shift under slow equatorial winds. The seas will sit still under their haze ceiling, dark and glassy and patient. The interior will flex under Saturn's tidal pull, warming isolated pockets of slush deep beneath the ice, cycling trace amounts of warm water through a labyrinth of high-pressure ice that may or may not ever connect to the surface. Nothing will change. Nothing will wake up. Nothing will begin. This is what Titan is. Not the most violent moon, not the most radioactive, not the most volcanically active, not the most immediately lethal, the most familiar. The most deceptively, structurally, hauntingly similar to the world where you were born, while being composed entirely of conditions that would end your life in a heartbeat. The scariest thing in the solar system is not a monster. It is not an explosion or a radiation belt or a volcanic eruption visible from orbit. The scariest thing in the solar system is a place that looks like home and is not. A place where your pattern recognition fires and your survival instincts should fire simultaneously, because everything your eyes tell you is contradicted by everything your instruments measure. A world of weather with no warmth, a world of seas with no water, a world of chemistry with no life, a world of landscapes with no light. Titan is Earth's dark twin, not because it is a copy, not because it failed to become Earth, but because it shows you what the shape of your world looks like when every familiar feature is rebuilt from the wrong materials, at the wrong temperature, under the wrong chemistry, in a place where the sun is a dim smear behind an atmosphere of poison and the nearest warm surface is 1.5 billion kilometers away. It is the moon that looks back at you with your own planet's face and says, nothing. Because on Titan, nothing has ever said anything, and nothing ever will. The reflection is perfect. The silence is permanent. And somewhere in the frozen dark beneath the haze, the methane rain is falling again.